Hello, this is Jacob. In this video, we're going to be talking about tracking of reference inputs. This video presumes that you already watched and understand the video on state feedback. So in that video on state feedback, what we learned was that using state feedback, if our system is controllable, we can use state feedback and place the system's eigenvalues wherever we want. So from a stability and time response point of view, that's good enough. If we can put eigenvalues anywhere we want, then we can make our system stable and we can make it whatever time response we want. But I didn't ask the question, answer the question, how do we make our output y go to some value that we want? And that's what we're going to talk about in this video. So if you remember in that video, we were talking about a single input, single output system. So in general, it could have many states, so something like this, but we're only going to consider a single input and only going to consider a single output. And we forgot about the problem of the D, having the D here. Most systems don't have it, and it's kind of trivial to include it. So let's just keep our conversation like this so it's nice and simple. So U and Y are both scalars here, and the feedback law that we talked about was changing U to be some reference minus some matrix K times our vector X. And if you remember, K was, in this case, a row vector that looked something like this, where you had values like this, and then our state vector looks something like this. So the combined thing is 1 by 1, so that you can subtract it from this thing, which is 1 by 1, to make our 1 by 1 U. So this was the state feedback law, and we said if we do that, we'll get this new system. We'll fundamentally change our system properties, and our system will look like A minus B times K. And if this doesn't look familiar to you, then please go back and review, plus B times R. So we have this new, effectively new input R, which is the thing we now control, and we have a new A matrix, and that A matrix we can place eigenvalues wherever we want. Now let's say that we have placed those eigenvalues so that they're stable. So now we know this thing is stable. This is an n by n matrix that's stable. And if we know it's stable, that means all the eigenvalues have negative real parts, which means none of the eigenvalues are 0, which means the determinant is not 0. So this new A matrix is an invertible matrix. We know that. We also know that if we give some sort of input in R, a constant input, let's say, step input, we know that because this is a stable matrix, that eventually the effect of the initial state will eventually decay away to 0, because this A matrix is 0, is stable. And so this thing is going to decay away to 0, and eventually all we're going to be left with is our forced response to our system. The natural response will eventually decay away. This is a property of stable systems that we've seen over and over in this class. And the fact that we have our new A matrix looks like A minus BK doesn't change that fact. This is just a new A matrix, and we know how to deal with systems like this. So if I give constant R, what's going to happen is eventually I'm going to go to some steady state X, where X is going to stop evolving, and I'm going to go to this steady state X. And what does steady state X mean? What steady state X means is that X dot goes to 0 eventually. Now this is going to happen as time goes to infinity. It's going to happen asymptotically. So we're talking about now this asymptotic behavior. But we know that in practice it doesn't really take from time to infinity. It really takes more like 4 or 5 time constants where you've effectively gone to your steady state value. So that isn't time at infinity at all. It actually be really fast, where to your eyes it looks like the system has stopped evolving and you've gone to steady state. So in this case where we've gone to steady state, let's substitute this situation into our governing equation out here. So X dot is gone to 0, and I have A minus BK, and I'm sorry, there shouldn't have been a dot here. And our X goes to X steady state, and our R is whatever value we set it at. So after 4 or 5 time constants, our system will asymptotically approach this situation here. And in this situation, because I know this matrix is stable, which means it is invertible, so I can actually invert this matrix. So I'm going to bring this BR over to the other side, and then I'm going to invert this matrix. And what I'm going to get after I do that is I'm going to get a solution for what my steady state X is. It's going to equal minus A minus BK inverse times B times R. I brought this BR over to the other side, so it became a minus BR, and then I multiplied by on the left side by the inverse of A minus BK. So that's my steady state X value. And I can find my steady state Y value by just looking at Y is just C times X. So that just simply equals minus C times A minus BK inverse BR. So I now know the value that my Y will go to if I give it some R. It will go to R times this thing. And this thing is a 1 by 1 thing, because C is a 1 by n thing, and this is an n by n thing, and this is an n by 1 thing. So this whole thing here, that's including a minus sign, let's make that clear. This whole thing is a 1 by 1 scalar. It doesn't include the R, like this. And we call this the DC gain of our system. So our steady state Y value, and I shouldn't have made this a vector because it's just a scalar, our steady state Y value is simply equal to the DC gain of our system times our reference. So from that, if you say, I have some desired steady state value that I want to go to, and you say, well, what should I make R? Well, if you want Y at steady state to go to some value, the way that you should properly assign R is you should make R equal to your desired value over your DC gain. If you do that, then you'll plug in that R into here, and the 2 DC gains will cancel, and your steady state Y will be your desired Y. So now we have a way to establish how we should choose R. This is the way we should choose R to make our output go to where we want it to go. Now, if you're critical here, you can say, well, is R always well defined? And I think the answer pretty clearly is, it's defined as long as our DC gain isn't 0. If our DC gain is 0, then my R would have to go to infinity for this to work. So this method that I've just shown you presumes that DC gain isn't 0. So the question is that a safe assumption to make? I think if you look down in the bottom left here, and you look at the way the DC gain is made, it seems completely possible that it could be 0. I mean, this is some n by n matrix, and depending on what my shape was in my B matrix, and depending on what's in my C matrix, I could easily imagine if there's some zeros in there in the right places, I can imagine this thing working out so stuff cancels each other out, and my DC gain could be 0. So it seems reasonable that my system potentially could have 0 DC gain, and then this process wouldn't work. It's typically not the case, but it seems possible. And so if we look at our transfer function, so let's look at our transfer function of our system. In the state feedback lecture, I was dealing with a 3 by 3 system, and so I'm going to stick with that example here. So with my original A matrix, if I have a 3 by 3 A matrix, my characteristic equation that I'm going to get is going to look something like S cubed plus I'm going to have some alpha 1 S squared plus some alpha 2 times S plus some alpha 3. And if I actually go through, that's my characteristic equation, if I actually go through and find my transfer function, again with my D matrix being 0, I'm going to get a strictly proper transfer function that looks something like, if I write my transfer function out, my characteristic equation is going to be in the denominator of this. And the numerator is going to be something strictly proper. So there's going to be an S squared term, and there's going to be an S term, and there's going to be a constant term. But the leading coefficient, even my leading coefficient of my characteristic equation, monic being leading by 1, that's not necessarily going to happen for the numerator. So let's call this some beta 1, and let's call this some beta 2, and let's call this some beta 3. So for those of you who've had a class on signals and systems, if you've taken a class on classical control systems, you'll remember that the DC gain is defined as g of s evaluated at s equals 0. And if I do that, this is the definition of the DC gain. If I do that and I plug in for every s I have in my transfer function, if I plug in a 0 for the s, I see that my transfer function, or my DC gain, excuse me, is beta 3 over alpha 3. And so right here you see, okay, I can see exactly that my DC gain can be 0, and the way that my DC gain is 0 is if beta 3 is 0. So GDC equals 0 is the same thing as saying beta 3 is equal to 0. And so if your transfer function, if the final coefficient on your transfer function is 0, then you're going to have a DC gain of 0. And this method of tracking that we described in the last slide isn't going to work for those systems. For that kind of system, we'll talk about that in the future. For most systems, that isn't going to be the case. That's not going to happen. And you're going to get something here that's a non-zero. And then the method for choosing R in order to make your output Y go to some desired YB is going to work for you.